Now that we've talked a little about the basics of electric charges and how they interact, it's time to move on to our primary example of that, which is electric circuits. Now in this class we'll stay limited to fairly simple circuits dealing just with batteries and resistors and wires, but even so there are some terms and some ideas that we need to be familiar with. Given the term electric current, it's not surprising that we often find ourselves using the flow of water, a current of water, as an analogy for electric circuits. So I've drawn here an analogy for an electric circuit using this sort of stair-step path that the water flows down, and then a pump to get the water back up. The pump here is representing a battery. And what that pump does is it takes the water back up to a higher height. Now, if it goes to a higher height, it would have more gravitational potential energy. Since we're dealing with charges going around a circuit in reality, we're not talking about gravitational potential energy, but electric potential energy. So the battery functions as an electric potential pump, moving these charges back to an area of higher electric potential energy. And then as they move through the circuit, we have these jumps right here and right here, where here our water, if we think in the water analogy, our water is at a constant height, so it has a constant gravitational potential energy, and then all of a sudden it drops very rapidly, and then constant, and then it drops, and it continues flowing here. And so those drops are going to represent what we call resistors. A circuit is typically going to be made up of components that are very, very low resistance to the flow of electric charges. Those will be our wires. And then other components that put up more resistance. Those are our components that do some useful work, or our resistors that are designed just to inhibit that flow of electric charges. But we notice that in between those two drops, we don't have any change in gravitational potential energy for the waterfall analogy, and on the battery end of things, on the circuit end of things, we won't have any change in electric potential energy except for at those resistors. So this diagram shows the same thing, but not as an analogy. We have our pump replaced by the battery. It takes these charges up to a higher electric potential energy, and then we have our charges flowing around the circuit. We have a drop across this little squiggly line that's going to represent a resistor, just some component with a high resistance to it, and then another drop here across another resistor, and then we get down here to our lowest potential energy, and the battery takes us back up. Now just a note about current. We think about current as, or we define current as the flow of positive charges. They leave the positive end of the battery and then travel through the circuit in this direction. We know that the positive charges are the protons, which are pretty well fixed in place. And so it's actually a movement of negative charges, of electrons, that's taking place here. So this idea of positive charges, it's really incorrect physically, but we didn't know that for a long time when we were describing electricity. So we call that conventional current. And on the AP test, the direction that current flows, they're talking about conventional current. So here we'll have that current flowing in this direction from positive to negative, even though we know it's really the electrons moving, and they move from the negative side of the battery to the positive side. So we kind of have to pretend that it's the positive charges doing the moving here. Now it turns out that it doesn't really make any difference for our calculations, whether it's the positive ones moving or the negative ones moving. But when they ask us about direction of current flow, we need to go from positive to the negative side of the battery. Now, this battery, we could have a variety of different potential energies that this battery provides, and that's associated with the voltage of a battery. So like a AA battery is a 1.5 volt battery, or the little square ones with the 2 prongs up top, those are 9-volt batteries. Now the voltage is going to be associated with the energy that we give it. So a 1.5 volt battery across here, that takes our energy up by 1.5 volts. Volts is really energy per unit of charge. So it takes our energy up by 1.5. The 9 volt takes us up by 9. So the 9 volt adds more energy to this system. And just like with the waterfall analogy, if we had our waterfall going up to a higher height, then we have more movement, we'd have faster movement, we have more energy in the system. So there are 3 terms that we're going to use with every circuit that you need to be really familiar with. The first is current. When we talk about current with water, we might use the terms a strong current or a fast current. What we're describing there is that there's a lot of water moving past a point very quickly, or a lot of water moving past a point in a certain amount of time. And if it were a slower current or a weaker current, we would have less water moving past some point. But here it's not water, but charges. And so for an electric circuit, we'll define current as not the rate of flow of water, but the rate of flow of charge past a single point. Charge we measure in coulombs, so the rate of flow of charge would be coulombs per second, or the unit you might be more familiar with there is amperes, amps, or just a capital A. Now, voltage, also called potential difference, deals with energy. And just like with energy, we care more about how energy changes from point to point than we do about what the value for energy at a single spot would be. So we don't ever really look at the voltage at a single point. We look at the voltage across some component or some set of components. The voltage across the terminals of a battery, for example, could be 1.5 volts. All that means is that the energy per unit of charge is 1.5 volts higher on one side than it is on the other. And so we define voltage or potential difference as the electric potential energy difference per unit of charge. So if we had a coulomb worth of charges going across this battery, a coulomb worth of electrons going across this battery, the difference in potential energy would be, if it were a 1.5 volt battery, we'd have 1.5 joules of potential potential energy change for that 1 coulomb worth of charges. And we don't really need to worry about having a certain number of coulombs. We'll work in the per coulombs unit. Joules per coulomb is the same as volts, which we abbreviate just with a capital V. Now the resistance is exactly what it sounds like. For all the components in our circuit, how much resistance do we have to the flow of these charges? If we go back to our water analogy, we might think about this as narrowing or widening the river path here. So if we have a narrow river, we can't get as much water going through that. Or if we change it to pipes, we'd have a narrower pipe. We can't get as much water flowing through that. So with resistance, we'll think of this as how difficult it is for charges to flow through either a single component or a whole circuit or part of a circuit, some collection of components. The units on this are joule seconds per coulomb squared, which is kind of a mouthful and not a real easily understood idea. So we just use ohms for this, and we abbreviate that with the capital Greek letter omega, the little horseshoe here. Now we actually define resistance as the ratio between the voltage across some object, some component, a resistor perhaps, divided by the current that goes through it. And so when we think about this, if we have a lot of voltage going through this thing, we should have a lot of flow through it. And if we have a lot of current as well, then we end up with a pretty small resistance. If we have a lot of voltage and a pretty small current, that means even though we've given it lots and lots of energy, we still don't have very much charge going through. That'd be a really high value of resistance. If we have just a little bit of voltage, so a little energy that we put in, and a very large amount of current, that means, well, it's pretty easy to flow through this. Look at all the charges that are going through, and we're not having to push at them very much at all. There's very little resistance to the flow of that. What we find is that for some materials that we'll call ohmic materials, this ratio is constant. So it doesn't matter how much voltage we put across this component, the ratio of voltage drop or potential difference across that component to the current going through it is going to give us just a single value. That value we define as the resistance R in ohms for that component.